All right, welcome everybody. This is the EC2 Instances Deep Dive. We've got two presenters today. I'm John, and this is Anthony. We'll introduce ourselves more throughout the presentation. Me first. So I'm John. I manage the team that defines and ships new instance types and new platform capabilities. Our team spends a lot of time talking to customers, sifting through usage data and trying to figure out what to build next. We drive the PR FAQ process, which is the Amazonian version of the product requirements document for new EC2 instances. And at the end of the day, we stay up most of the night during launch calls to make sure everything runs smoothly so you have a nice email the next day with something new from EC2. Today we're going to talk about three things. The first is what is the EC2 instance platform and a little bit of a virtualization primer. Anthony will talk about how to make the most of your EC2 instance experience to kind of ensure that you walk away with some valuable best practices and get a lot of value out of this presentation. And then I'll jump back in and talk about how do we think about the future of EC2 instances in the platform. So Amazon EC2 is extremely broad. Back in July, I gave a talk at the New York Summit. It was the Introduction to EC2 talk. And it turns out that's a really tough talk to give, primarily because there's so much to cover. You've got our APIs, you've got our networking, you've got purchase options and pricing models, you've got things like Amazon VPC and EBS, and then you've got the hardware and the instances themselves. And in this presentation, it's going to be a lot more focused. It's going to be more like hitting the zoom button over and over again on the hardware until we get into the virtualization layer where you can really understand what's going on and how to make the most of your EC2 instance experience. There are a number of other important things that are a part of the EC2 platform which are not going to be covered, and I wanted to give them a brief call out. There's an EC2 networking deep dive and best practices talk given by Becky Weiss. That's today at 3:30 p.m. There's a VPC deep dive by Kevin Miller. That's Friday at 10 a.m. There's a purchasing options deep dive and best practices provided by Steve Elliott. That is today at 4:30 p.m. And then there's an EBS deep dive presented by Dougal Ballantyne. That's tomorrow at 1:15 p.m. So as a review and level set, here's how you should think about EC2 instances. EC2 instances are virtual machines that are spun up when you issue an EC2 run instances call or an EC2 start instances call. We find available hardware with the right type of capabilities. We signal to the hypervisor to spin up a virtual machine, and then we pass along the SSH key or Windows administrative password so you can do as you please. Servers often have more resources than the instances need. So you can end up, you can end up on a host with either more than one instance or one instance depending on the instance size. And today we're going to focus on this layer, but pointing out here that the guest is the EC2 instance. Zooming in further, when we differentiate and group instances into families and generations, these are the specifications that are the drivers of this differentiation. Over time, we've built a portfolio of instances optimized on one or more of these dimensions. Some have more CPU, some have more memory, some have lots and lots of storage or I/O, some have accelerators like GPUs. If you take us back to 2006 when we ran the EC2 beta, we had one instance type, and that's the M1 small, and now we have over 30 to serve a diversity of workload needs. So getting the most out of EC2 comes down to a lot choosing the right instance type for your workload need and then focusing on that resource that serves as the bottleneck for you. And the specification is mostly reflected in our API name, and this is just a quick review. These terms will come up often in the remainder of this presentation. But the first character or two characters of the API name signify the instance family, which indicates which resources we're optimizing for, C for compute optimized and high CPU. The second character or third, depending on how many letters there are, indicates the generation. We use new instance generations to provide you the latest platform features or technologies that are important to a specific instance family. So with the compute family, it's the latest generation technology and processors. For memory. For storage, it would be something else. For GPUs, it would be latest GPUs. And within each generation or instance type, there are multiple sizes. And again, getting the most out of your EC2 experience means picking the right size for your workload and the right family for your workload. Zooming in even further, and now we're into the virtualization layer, I wanted to provide a brief primer. Since EC2 launched, the industry has made some advancements in virtualization, which are important background for understanding EC2 instances where we take the product. First, let's look at X86 CPU Virtualization. One of the keys here is that the hypervisor must trap any instruction that changes the hardware state of the system. And the X86 instruction set has a few instructions that make this challenging. Before Intel released VTX, which is a hardware-assisted virtualization technology, there were a couple of options. One was to have the hypervisor scrutinize the instruction stream from each virtual machine, look for these instructions, and emulate them using binary translation. That was a resource-intensive task, so it came with a performance penalty, but it meant that you didn't have to change anything in the guest operating system. An alternative to that is you could tell the hypervisor to completely ignore these challenging instructions and instead replace them with hypercalls. This offered better performance and is known as para-virtualization. So this offers better performance, but it required guest OS modifications. Intel VTX introduced a new CPU execution mode, which meant that you could both get performance and do not have to modify the guest operating system to get that performance. So it came with performance and flexibility. And this is actually known as HVM, and you can see this surfaced in our product offering with Amazon machine images, para-virtualized images, and then HVM Amazon machine images. We actually support HVM Amazon machine images with our newest instance types, and we support HVM only. So you've got T2, R3, and I2 that are HVM only instances to reflect this progress in virtualization technology. Now, another thing to think about with CPU virtualization is the scheduling choices that you have. The naive approach to scheduling vCPUs actually results in variability. And this is to let the hypervisor schedule virtual CPUs to physical CPUs as needed, rather than doing something like direct assignment or pinning, or providing some other control mechanism to increase consistency and predictability. Consistency is very important to us, and we think there's a great opportunity to maintain consistency whether you're looking to maximize performance through something like direct core assignment to a virtual machine or minimize costs. So that's a little bit about X86 CPU virtualization. Consistent performance is also one of the challenges of providing I/O to virtual machines. I/O requests from virtual devices must be scheduled across shared hardware, physical hardware. And what's commonly used is a split driver model where hardware-specific drivers reside in a control OS, and a simple front-end driver resides in the guest OS and communicates back to the control OS through a back-end driver. It's the responsibility of the host then to multiplex and schedule these I/O requests from various virtual machines. That process can require host resources, and that can also cause some variability. One option to deal with this variability, as virtualization technology and landscape has evolved, is to do a pass-through a device directly to the virtual machine. Historically, one of the challenges to doing that is direct memory accesses. And that means that a device can modify system memory without bothering the CPU. In a multi-tenant virtual environment, that's a little bit dangerous because you want to maintain isolation. So what And the evolution of virtualization technology, Intel now offers Intel VTD, which provides for direct pass-through of devices to virtual machines and through an I/O memory management unit, among other things. So it can do memory address translations through the use of page tables. And this is how we enable PCI pass-through for things like GPU instances, and you can pass through other devices using similar technologies. So what do these trends mean to us, and how do we think about these as they relate to our instance platform? We really have a philosophy of no compromises. We want to offer you faster, bigger, less expensive instances that offer operating system flexibility and consistent performance. Our bar is really bare metal performance, and you, our customers, help us prioritize our roadmap, which is the path to bare metal performance. We're going to look at how we respond to these trends. Anthony will come up here in a second through the lens of a couple of recent platforms, T2, I2, and C3. And to guide you through the next section of this presentation, you'll see a lot of these pointers. This is where we are going to indicate that we're giving you something we think is valuable to make the most of your EC2 experience, the tips and tricks or best practices. We care a lot about customers getting the most out of our EC2 instance experience. And with that, I'll hand it over to Anthony.
All right. Thanks, John. My name is Anthony Luger. I'm a principal engineer in the EC2 kernel and operating system team, and I have an awesome job. My job is to make EC2 instances as fast as possible, robust, and secure. And one of the things that I like the most about my job is talking to customers and helping them get every little bit of performance possible out of their EC2 instances. So for the rest of this talk, I'm going to walk through 3 platforms and make a couple suggestions for each platform about how to make sure you get the most out of it. But this is really just scratching the surface. And I'll be here for the entire week of the conference, and I'd love to have more conversations about how you're using EC2 today and also how you can get the most out of EC2. So to start with, we're going to talk about the T2 instance type, which Andy talked about a little earlier in his keynote today. And T2 is a burstable performance instance, really suited towards general purpose workloads, and it's our lowest cost instance by far. The really interesting thing about T2 is that we offer it in 3 sizes, but the small and the micro, the difference between the amount of CPU available isn't the number of vCPUs, as is the case in most of our instance types, but rather the number of CPU credits that you earn per hour. And this is the only instance type today that we talk about in terms of this concept of CPU credits. And the very first tip that we have, and I tried to start with a nice easy tip, is make sure you understand what CPU credits are, how they affect your workload, so that you can optimize your workload and choose the right T2 instance to fit your workload type. So there are 3 resources that I have on this slide, and these slides will be available on SlideShare, so you don't have to try to type all of this down. Jeff Barr's blog, he had a really nice explanation of how the burstable performance works on T2. The instance documentation for T2 on the website also has a really good explanation. But then also, if you just attend the session, which you're already doing, you get this tip for free. So congratulations, you've already implemented one best practice. So the way that the T2 instance performance works is via a mechanism called a credit bucket. And the credit buckets, the best way to think of them are like literally if you have a bucket and it's all about how you place balls into a bucket and pull balls out of a bucket, and the rules around how often you put new balls into a bucket and how often you pull balls out of the bucket. And for any computer science majors in here, you spend weeks and weeks and weeks in classes talking about all of the different strategies for implementing these token buckets, but we're just going to focus on the way that we do it within the T2 instance type. So the first characteristic dimension of our credit bucket implementation is the fill rate, or the baseline rate. So on the T2 micro, it earns at a rate of 6 credits per CPU hour. So for every hour you're running, you essentially put 6 balls into the bucket. And we call this the baseline performance. And we've very carefully thought through this baseline performance to make sure that it was a good level of performance for a lot of workloads. However, the thing that makes the T2 instance special is the rate that you can withdraw credits from the bucket. And we call this the burst rate. Now, in the best case scenario, when your credit bucket is completely full, you can withdraw credits basically as fast as you want to. And each credit represents 1 minute of CPU time. So if you have a completely full bucket and you run flat out at 100% CPU, in 5 minutes you will withdraw 5 credits. That's the way that the credit system works. Now, at some point, the bucket is empty. And when the bucket is empty, the rate that you can withdraw becomes the rate that new credits are added. And one of the things that we wanted to make sure of when we implemented this mechanism is that you didn't see a sudden drop-off in performance. That if your workload was running and you got to the point where you were running low on credits or ran out of credits, we didn't want the results to be catastrophic. So the rate at which you can withdraw credits is proportionate to the size or the fullness of the credit bucket itself. The other characteristic of the bucket worth mentioning is that credits do expire over time. And one of the characteristics of a bucket is that at some point it gets full. And if you keep adding to it, it's just going to spill over. And credit expiration is our way of attacking that problem, that over time the credits sort of magically disappear. So we did a few other things to try to make sure that your workload, or that this mechanism worked very well for a wide variety of workloads. We made sure to start your credit allocation with a good fill rate. When you launch an instance for the first time, you do a lot of things like boot, start up your services. You tend to do CPU-heavy activities early on. So we wanted to make sure that you got a really strong credit balance so that you could burst from the very start of day for your application. And then the other thing that we did is also really important is we tried to be extremely transparent about this mechanism, not just how it works, but also what your current credit balance is, and so that you can use this to rationalize about your application. And this leads to the second tip, and that's actively monitor your credit balance and how it affects the performance of your application. So this is a CloudWatch graph that I borrowed from Jeff Barr's blog that just shows you the mapping of instance credit usage versus the size of the bucket. And you can see the behavior in this graph. I guess the lines are large enough that I described earlier, whereas you start out with a nice, healthy credit balance when the instance launches. And then the orange line that sort of peaks and goes down is where Jeff kicked off a heavy CPU workload. And you can see that it starts using credits at a pretty fast rate, and it sustains that credit usage for some period of time. And then at some point, it's a little hard to see, but the credit balance declines, and the rate at which you can pull credits, again, starts to decline. But fortunately, the application finishes before you exhausted your credit balance. So you got to burst for pretty much the entire time, and you got really, really good performance in this workload. After this activity is finished, the credit balance starts replenishing, and within a few hours, you get pretty close to where you started from. So what you want to look for when you're looking at your application and you're looking at your credit balances and usages is that the peaks that exist in your application, whether it's from peak hours or because it's a batch workload where you're running jobs periodically, that during those peaks, you're not exhausting your credit balance and running at just the baseline performance. So the T2 instance is really great for a wide variety of workloads, particularly ones that benefit from burstable performance. On the other side of the spectrum, there's the I2 instance, which is also one of my favorite instance types. And this is our instance designed for high-performance databases, particularly NoSQL, or really any workload that requires really low latency disk access. So the largest I2 size, the 8X large, has 800 gigabyte SSDs attached to it and can drive 365,000 IOPS, which is really just it's an amount of I/O that every time I see it in an instance, it still excites me, even at this point in time. Now, the thing that's really interesting about a platform like this is that if you just take, a random Linux distribution or a typical workload, the workload's going to be challenged to drive this much I/O. It really does require some tuning within the instance to fully make everything you can out of this platform. And I wanted to talk a little bit about what the things are that you need to do to really get the most out of a platform like the i2. The first tip is to make sure you're using at least the 3.8 kernel version. So the 3.8 kernel introduced a number of features that without those features, you just won't get this IOPS rate. And fortunately, every version of Amazon Linux AMI since 1309 has these features already. So if you're an Amazon Linux user, you're already covered. Ubuntu 14.04 in later versions also have this feature. So if you're an Ubuntu user using at least the 14.04 version, you're covered. RHEL 7, which is probably the newest commonly used Linux distribution to add these features, also has these features, and that also carries over to CentOS 7. And if you're using another distro, just make sure that the kernel version is at least 3.8. Now, this is information that we have on our website, and I get a lot of questions about, do you really need this kernel version? What happens if you don't use it? And I wanted to talk a little bit about why we make this recommendation and explain how the underlying technology works. So prior to the 3.8 kernel, every time your instance wanted to do some I/O, for instance, at some layer on Linux, something's going to make a read system call. It might be through layers of Java library, or it might be written in assembly, but something is going to do a read system call. And it's going to have a memory buffer that says, I want to read data to this location in memory. Now, instances don't have direct access to their underlying SSDs. This is one of the ways that we secure the platform. This is one of the ways that we can offer all of the features that we offer. But if the instances don't have direct access to the SSDs, how do you actually do that I/O to that memory location? What we have in EC2 is we have this special instance that we call the I/O domain. And the I/O domain is the thing that actually has access to the underlying hardware and that can actually do DMA operations to the physical disks. And in order for the instance to do I/O, the first thing it has to do is it has to give permission to the I/O domain to access the memory that you want to do the DMA operation to. By default, the I/O domain does not have access to the instance's memory. So the instance has to explicitly grant permission. And because virtualization developers are particularly clever, this is called granting. And when the I/O domain actually maps that page and can access it, we call that a grant mapping. Now, this is a really cool mechanism. It's really fast at moving large amounts of data. The challenge, though, is that every time you do one of these mappings, it involves something called a TLB flush. And TLB flushes are very, very expensive under certain circumstances, particularly if you're doing many of them. And 360,000 per second definitely counts as many TLB flushes. And if you're doing that many TLB flushes every second, you're going to have problems. So, as is often the case in computer science, the thing that doesn't seem intuitive actually turns out to be better. And in this case, there's a feature in the 3.8 kernel called persistent grant mappings. And the way it works is that instead of giving permission to every single piece of memory that the instance wants to do I/O to, it pre-agrees with the I/O domain on a pool of memory that the I/O domain always has access to. And the instance uses this as effectively a bounce buffer. So every time you want to do I/O, instead of granting permission to access that page, you pick a location within the persistent grant pool, you do a copy into the persistent grant pool, and then you tell the I/O domain about that location. So instead of doing these TLB flushes, you instead are doing data copies. It turns out that modern processors are really, really good at copying data, particularly if it's hot data, if it's data that's been recently accessed. And there's almost a doubling in IOPS performance using this copying mechanism over the remapping mechanism. So this is the main reason why we recommend the 3.8 kernel. And you can still have a really great experience on i2 without the 3.8 kernel if your application doesn't need to drive this level of IOPS and you really just care about latency. But if you are trying to drive really high IOPS rates, you definitely want to have this feature enabled. Second thing about i2 that I very frequently get asked about is trim. So if you have heard about, or if you're deep into SSDs, you've certainly heard about trim and discard. And this is a relatively new operation that was added to support SSDs. And in terms of what you need to do, it depends somewhat on the AMI that you're using. But the fstrim command is the easiest way to just go through and issue trims everywhere that needs to be issued trims. You want to do this periodically. You don't want to do this all the time. Like once a day or even once a week will make a big impact to your workload. Trim support is relatively new in Linux. Very old kernels do not have trim support. So if you're not able to do trim, or if you're running Windows, the Windows drivers today don't support trim, then the other option that you can do is something called over-provisioning. And it has the same effect as trim. And the basic mechanism is you reserve 10% of the disk, and you just never touch it. So the easiest way to do that in Linux is to create a partition and just never touch the partition. I'll admit I'm a Linux user. I have no idea how to do this on Windows, but if I did, I'd have some pretty GUI to create partitions, but it's the same basic idea. So why do you need to do this? Why is this important? Well, it turns out that SSDs are really sophisticated devices. And it's due to the fact that the underlying technology that powers SSDs, called flash, has some interesting physical characteristics. Namely, it wears out over time. Every time you write to a sector in flash, it degrades a little bit, and eventually, after thousands and thousands and thousands of writes, it just stops working. Now, the thing that's really, even though that rate is really high, if you think about a typical application like a database might be rewriting like the transaction log over and over and over and over again for almost every single I/O. And if you just took the naive approach to just mapping writes directly to the corresponding sector on the disk, you would wear out that sector really quickly relative to everything else. So SSDs implement a technology called wear leveling, and that's really the source of all of the interesting things that we're going to talk about here. And it really comes to any time you have a large, complicated software stack, there's always special things that you're going to have to consider. So trim and over-provisioning help avoid garbage collection. And if you're a Java application developer, a Ruby application developer, then garbage collection should be very familiar. And this is essentially what you're trying to avoid with trim and over-provisioning. So to really, really briefly dive into this, given time constraints, the basic way that SSDs work is they take the entire disk and they treat it as a large ring queue. And the way to think about a ring queue is if you take a piece of string and you tie it together, and then you hold one place in the string with one hand and hold another place on the string with the other hand, every time you do a write, you advance these one set of fingers, right? So every single write that you're doing, even if you're writing in place, you're not actually writing to that sector. Instead, you're always appending to the end of the ring queue. And this is one of the reasons why SSDs have this really cool characteristic that sequential writes are roughly the same as random writes in terms of performance, because they're the same thing. There is no difference. all writes get converted into these append operations to the transaction log. Now, the great thing about this is that it means you very evenly wear out the SSD, because every write writes to a new location, and you have really, really good endurance using this mechanism. And as long as there's plenty of space left on the string, everything goes well, everything's solid. However, in practice, at some point, you're going to wrap around the string, and you're going to have to deal with the fact that you can't just write to the end of the SSD anymore. And what ends up happening is that you're going to have a certain number of blocks that have data on them that you still have to preserve, even when you want to do a write at the tail point of the transaction log. And you really have two choices here. You can search forward, and you can try to find a free block on the transaction log. And obviously, that means that you're going to have to do more I/O on the disk, and the result is going to be a pause. It's just like garbage collection in JVM. The other thing that potentially has to happen is you might decide to move blocks around to free up space closer to the tail. And this is called write amplification, where you're doing a single write operation, and it might get turned into 2, 3, 4, et cetera, write operations. And obviously, that's going to really decrease your write I/O capabilities. Now, just like with a JVM, if you create an application in Java and you size the heap at 1 gigabyte, you don't want your application to try to allocate 1 gigabyte of memory. If you do, you're going to have garbage collection all the time. You're going to have really bad performance. You try to size your application to only use a percentage of the heap, maybe 80%, 90%, and that gives enough free space that when you need to do an allocation, the JVM doesn't have to do that much work to actually do the allocation. It's the exact same thing with SSDs. Over-provisioning is just leaving the disk with enough head space that it doesn't have to do garbage collection that often. And trimming is really just a way to tell the SSD where free space already is, and it has the same effect as over-provisioning, but it's just more dynamic. In practice, trimming versus not trimming can double, triple, even quadruple your write IOPS rates. So it's a really important thing to do if you have a write-heavy workload on an SSD. Now, continuing with the theme of our high-performance instance types, the C3 instance type is our high compute, and it is where you can get the most compute cycles today within an EC2 instance. It has a 2.8 gigahertz processor. It's 3.2 gigahertz with turbo, and it also introduced enhanced networking, which can give you the highest possible network performance within EC2 with the lowest amount of variability and jitter. And there's a couple things that I often find are important to do to really get the most out of a C3 instance. The first is to use HVM, and this is something that very frequently I get asked about, and it's an area where you can really see a big performance improvement often with very little effort. So with Amazon Linux, the very first column in the matrix is HVM with EBS. That's because that's what we want you to use. So that's why it's first, and it definitely is going to give you the best experience. So John talked a bit about HVM versus PV, and I just wanted to go into what makes HVM faster. Why does it actually impact your workload? And on a normal bare metal server, there's really two privilege modes that the system is running in. It's either running in the kernel mode, or it's running in a user space mode or application mode. And depending on what your workload's doing, it may have to make a large number of requests from the user space application to the kernel, either to do I/O, for timekeeping purposes, for a large number of things. And fortunately, Intel has done a really good job optimizing this, so it's very, very fast today. I like to say that you can do, the time it takes to do a system call is roughly a handful of division operations. So in terms of orders of magnitude, often doing math is more expensive than making system calls. And a lot of applications have come to rely on this. Now, When virtualization was first introduced, when EC2 was first launched, we only had these two privilege modes to work with. There wasn't any special hardware support for virtualization at the time, and particularly for 64-bit PV guests, whenever an application needs to talk to the kernel, instead of being able to go through this very, very fast hardware channel for the communication, it actually has to talk to the hypervisor. And the hypervisor has to mediate the communication between user space and the kernel. And this mediation requires a TLB flush. And like I mentioned earlier, TLB flushes are generally evil and should be avoided. So for some applications, it won't make a difference. If your application is largely doing user space computation, then you might not see a difference between PV and HVM. However, if you are using a lot of I/O, if you're sending a lot of packets over the network, if you're making a lot of kernel interactions, you can see I've measured as high as a 2 to 3x performance improvement from using HVM over PV. So it really can make a big difference for your application. And the final tip we have for getting the most out of your C3 instance is to use the TSC as your clock source. On Linux, there's two different time mechanisms to know about: clock source and clock events. And at a very high level, when you do a get time of day, you're accessing a clock source. I have commands on the screen, and you can see it on the slide share after this event, that will let you see what your current clock source is. Usually, by default, it's going to be the Zen clock source, the Zen PV clock. If you're running on C3, or if you're running on any of the current generation EC2 platforms, you definitely want to use the TSC as your clock source, and you can do that by modifying your kernel command line parameter. You'll notice that I used Emacs for that. That's also very important because it is the right editor to use. You'll be much slower if you do it with VI, I swear. So timekeeping is a really, really fascinating topic. If anybody runs into me in any of the after events, I can talk for hours about it over beer, and it'll be a great conversation. But the important takeaway for this talk is that it's deceptively hard. And deceptively hard means there's a lot of software involved in figuring out what the current time is. So if you have an application that's doing get time of day, or on Windows the equivalent is query performance counter, then this will affect you. And the types of applications that typically do this, if you're doing JVM tracing, it does very, very heavy get time of day calls. If you're doing benchmarking, oddly enough, benchmarks tend to measure the time of every single I/O requests, and so benchmarks tend to show this problem more than a lot of applications. Then this will help you out a lot. Without going through the gory details about it, the TSC is a hardware clock source that basically gets rid of all of the ugly software that typically has to go on top of things. And the most important thing is that on Linux, you can access the TSC without even talking to the kernel. And so avoiding that system call can make a big difference for certain workloads. Now, there's a really good reason why the Zen PV clock is the default clock source. It's because that's the thing that gives you the best compatibility across a whole wide range of hardware. But when you're running on EC2, we have very well-defined hardware, and our hardware is always going to be compatible with the TSC if you're on a current generation platform, at least. So with that, as I mentioned, this is just a small number of the tips we have, but I'll turn it over to John to close us out.
Thanks, Anthony. So we're really just scratching the surface. Lots of tips and best practices in this presentation. Using a 3.8 plus kernel for grant pooling to deliver high I/O, getting the right time source is important for, especially if you're doing things like benchmarking. We've got a lot to talk about. If you wanted to follow up after this, come visit us at the developer chat afterwards to hear more. And of course, visit the EC2 instance documentation for more information, more tips and tricks. And I wanted to leave you with a final note that kind of brings us back to the surface. which is the future of EC2. We have a platform that allows us to ingest new hardware and new technologies and work that smart folks like Anthony does to customers in the form of new instance families and new instance generations within each family. And there are more of those to come in the future. So what I'd like to leave you with is just the request that you come to us and you tell us what you want the future of EC2 to look like, because we have a platform that we can take your feedback, and we take your feedback very seriously to improve our offering. Thank you very much.